In this lesson, we're going to be looking at derivatives and their graphs. Right, so here I have three graphs. The first graph is the graph of y equals 3x cubed plus 6x squared minus 2x minus 2. It could be a position function. Right? It's our function there. So if this is position function, it would find the position at a time, like a maximum or a minimum. Right? So if you want to find a y value for a given x value, you would use your position. You would use your function. This is cubic. If we look at our graph here, we have two places where we have horizontal tangent lines. It's kind of hard to tell what those are. Maybe it's like maybe 1.8, or negative 1.8 or so, and then maybe, I don't know, a fourth. But there's two places, you notice, where we have horizontal tangent lines. We have a place where we have a change in concavity, right? The first part of the graph here, this part is concave down. And this part here is concave up. So we change concavity, just about at -1, a little bit less than -1, maybe negative 0.8. All right, so if we take the derivative, the derivative of 3x cubed plus 6x squared minus 2x minus 2 is 9x squared plus 12x minus 2. All right, so the derivative finds a rate of change at a point. It's the slope of our tangent line. Right? We use that to find rate of change. All right, so let's compare the graph of the first derivative with the graph of the original function. Right? Well, everywhere we're above the x-axis on our derivative, that's going to correspond to where we are increasing. Right? So, kind of wrote over it a little bit, but so here we're increasing, and that matches with here we're increasing. Okay. Now they're not necessarily drawn to the exact same scale because I may have cut off a little piece of it. So it may go up a little farther, but it may have gotten in the way of the other graph. But wherever it's increasing on the function corresponds to where it would be positive for our first derivative. And likewise, we're also increasing right here. Right? So our first derivative is going to be positive as well over there. But in between, from here to here, our function is decreasing. Notice that corresponds with where our first derivative is below the x-axis, where it's negative. Notice we have zeros in our first derivative, right? And notice they match up with where we have horizontal tangents in our function. So a horizontal tangent in our function corresponds to a 0 in our derivative. It's an x-intercept for our derivative. So if we're looking at the graph of a derivative, all of our x-intercepts indicate max and mins in the original function because the slope of the tangent line is going to be 0. And the derivative measures the slopes of the tangent lines, the rate of change. All right, so zeros in the first derivative correspond with horizontal tangent lines in the original function. Could be a max, could be a min. Right? Whether it's a max or a min depends on whether if we go from increasing to decreasing or decreasing to increasing. So notice that we went from, if we look from left to right, we went from increasing to decreasing. That's going to be a max. Then we went from decreasing to increasing. That's going to be a min. All right, so you should be able to look at the graph of the derivative and know where you have horizontal tangent lines, where you have max and min values, where your original function is increasing or decreasing. Okay. All right, now let's look at the second derivative. So if we take the derivative of 9x squared plus 12x minus 2, we get 18x plus 12. Your second derivative indicates concavity. So you use your function to find position. You find that to find y values, points on the function. You use your first derivative for rate of change and your second derivative from concavity. All right, so notice that we have a 0, we have an x-intercept for our second derivative when we graph it. That corresponds with a point of inflection, right? So where we have a change, and actually let's go all the way up to the 3 graphs. Where we have an x-intercept on the second derivative, we have a, I wish I could point to it. I need a pointer or something. Can't. I can have a little arrow moving around. So where we go, here's, now I can, oops, if it moves, I can point. So watch my pointer. Where we have an x-intercept on the derivative, on the second derivative, we have a horizontal tangent line on the first derivative, right? And then we have a point, come on arrow, we have a, whoops, too far, a point of inflection on the original function. So notice how those things all go together. Okay. So where we have an x-intercept indicates a change in concavity in the original function if we change signs. So where we're below the x-axis, we're concave down. Where we're above the x-axis, we're concave up. So we can use our second derivative to tell about concavity in our first derivative. I mean, in our first derivative, in our function. Okay. All right, let's look at some more. So this whole lesson is going to be looking at functions and the graphs of derivatives, first derivatives and second derivatives, and being able to draw the graph of the derivative from the function and the function from the derivative, and going back and forth. So functions and the derivatives. In order to see the connection between a graph of a function and the graphs of its derivatives, we're going to use some graphing technology to generate graphs of functions, I already did that, and simultaneously generate a graph of its derivative. Then we'll connect concepts like max and min, increase, decrease, concavities of the original function, and what we see on the graphs of its derivatives. And by the way, there are some problems in here that would make excellent notes. I will post those so that you can print them out. I'll tell you when we get to them. All right, so here we have f of x, f prime of x, and f del prime of x, all graphed together. So on the same scale this time. All right, so here the red graph is the original function. That's f of x equals x squared minus 4x minus 5. Its derivative would be 2x minus 4. That's the blue line. And then the derivative, the second derivative, would be the derivative of 2x minus 4, which is just 2. All right, so now let's take some look at some things. All right, so on our original function there, we have, and I'm grabbing my pointing arrow. Come on, pointing arrow. Hello. That doesn't look like a pointing arrow. Sometimes it doesn't like to write if I have a picture. How about now? There we go. It didn't like me writing over the picture, I guess. Come on, arrow. Woo. There we go. All right, so watch the moving arrow. Oops. You can't grab it. There we go. All right, so no. Go back down. No, spinning ball of death is wrong. Just wrong. Come on, arrow. All right, well, you see me point. You can't see me pointing, but see the minimum. All right, so where we have a minimum on our graph corresponds to, maybe the arrow will move up. Arrow, you're failing me. The other arrow works so much better. Corresponds to an x-intercept on our derivative, right? Right, so that's going to be a 0 because what does the first derivative measure? It measures our rate of change. And where we have a minimum, we have a horizontal tangent line. And where we have a horizontal tangent line, our rate of change is 0. So that corresponds to a 0 for our derivative. Where our function is decreasing, decreasing, the fun part of the roller coaster, our graph of our derivative, our first derivative, is below the x-axis. Where the function is increasing, going up the hill, right? Where it's increasing, our graph of our derivative is above the x-axis, right? So we can tell just from the derivative, the graph of the derivative alone, that this has to be a relative min because we go from decreasing to increasing, all right? So just from that, we can tell what kind of relative extrema we have. If we look at the very exciting graph of the second derivative, it is all above the x-axis, right? So positive, so that means we are concave up everywhere, and you can see from the graph that that is true, right? And since there are no x-intercepts, there are no changes in concavity. Function is always concave up. All right? So here we can take a look at all three of them together, and what does each one of them tell us about the other. And then we're going to talk also about what happens when we have let me point it out now. So I won't mention it, but I'll just kind of draw your attention to it and I'll mention it later. So notice that my derivative is increasing everywhere, right? The function's not, but the derivative is, right? It's a line, right, with a positive slope. Notice that my function is concave up everywhere. Right? That's all I'm going to say on that. All right, so some points to notice here. They all are together, except for the second derivative. And the second derivative was just so straight, a kind of straight line, right? So this is f double prime of x, and that was 2. Ugh. I should have reoriented the board before I started recording. F double prime of x equals 2. It comes up so much after I finish writing, or maybe not at all. It's mad at me because I said the writing was icky. There we go. All right, so def double prime of x is 2. That's our, so we're concave up everywhere. All right, so the function has a minimum at x equals 2, and the derivative has an x-intercept at x equals 2. The function decreases negative infinity to 2, and the derivative has negative values, negative infinity to 2. The function increases from 2 to infinity, and the derivative has positive x values, excuse me, I shouldn't say x values, positive y values, positive values on 2 to infinity. The function changes from decreasing to increasing at the minimum, while the derivative values change from negative to positive. The function is concave up, and the derivative function is an increasing function, everywhere increasing. All right, so see how they connect together. New graph example 2. All right, so this time, and look at all that stuff in there. I think I put this one in your notes. So much stuff to pay attention to. I had to type it. Otherwise, there would be just, you'd have to read it and it wouldn't be pretty. All right, so the original function is the red one, right? The cube, obviously, has to be the cube because you lose 1 degree every time you take the power rule. All right, so the original function is somewhere on this board. Where is it? Oh, there it is in red. F of x equals x minus 1 times x plus 2 times x plus 4. I did multiply that together because I did not want to have that, take the derivative of that. You don't want a product of 3 things. I don't even know what to do with that. That just wouldn't be pretty. There's no reason not to just simplify that up a bit. All right, so that's f of x equals x cubed plus 5x squared plus 2x minus 8. A lot easier to deal with. All right, so the derivative, it would be 3x squared plus 10x plus 2. And of course, the second derivative would be 6x plus 10. All right, so let's compare. Original function, we have a relative maximum there at negative 3. I don't even think I think I can label, well, maybe I'll move my arrow. I was thinking I can just say the values. There's so much up here, but I'll just draw a little tiny arrow. He won't get in the way. He may not move, but he won't get in the way. So we have a relative maximum here at negative, now my shadow was blocking, negative 3, and that corresponds to an x, well, almost negative 3. And that corresponds to an x-intercept at almost negative 3. Right? Our function is increasing from negative infinity to almost negative 3. And our first derivative is positive from negative infinity to almost negative 3. Right? Then our function is decreasing from negative 3 to, my shadow's blocking again, to, I can't see the value. Oh, whatever that looks like to you, 6 something. I can't tell. My shadow's blocking, and I'm not sure if I even see a number up there. All right, so we're decreasing from there to there, and then we have a relative minimum. So notice we go from increasing to decreasing. Right? So that's going to be a relative max, and our function is above, below. Right? So now it's a relative min. So now we have a x-intercept for the first derivative, right? And once our function starts to increase, our first derivative is above the x-axis. Okay? All right, let's look at concavity. So we are concave down. Oops, arrow's going all over the place. Concave down to this point here, right there. Do you see the change in concavity? We're turning, right? So right there's our inflection point. That corresponds with an x-intercept on for the second derivative. Notice where we're concave down, the second derivative is negative. At the inflection point, we become concave up. And where we're concave up, the second derivative is above the x-axis. It's positive. Right? Notice one last thing. So, our derivative. So our derivative is decreasing, 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 decreasing to right here. And our function is concave down, concave down, concave down, concave down, concave down to right here. Now our derivative is increasing, 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 increasing. And our function is concave up, concave up, concave up, concave up, concave up, concave up, concave up. I'm hoping you get making the connection here. I actually think this is working out better with my moving arrow because I can stand right in front of the board and move the arrow. I'm not blocking anybody. You can all still see. All right, so f of x has a maximum at x equals negative 3, and the first derivative has an x-intercept. At negative 3.1. That's what almost 3 was. At negative 3.1, and the derivative has an x-intercept at x equals negative 3.1. F of x has a minimum at x equals negative 0.2, and the function has a root at negative 0.2. So that's where we were located. My hand was blocking so badly I couldn't see the scale at all. Our function increases from negative infinity to negative 3.1 and from negative 0.2 to infinity. I forgot we were at negative. I didn't even notice the x-intercept, the y-axis, because my hand was blocking the screen. On the same interval, our derivative has negative values. At the max, x equals negative 3.1. The function changes from being an increasing to a decreasing function. The derivative changes from positive values to negative values. And at the minimum, x equals negative 0.2. The function changes from decreasing to increasing. And the derivative changes from negative to positive. The function's concave down from negative infinity to negative 1.67, while the derivative decreases from negative infinity to negative 1.67. The function is concave up on negative 1.67 to infinity, while the function the derivative increases on negative 1.67 to infinity. Do you see a relationship between these? I hope so. The concavity of our function increases from concave down to concave up at x equals negative 1.67, while the derivative has a minimum at x equals negative 1.67. I forgot to mention that. So our inflection points correspond with max and min values for our derivative, depending on which way we're changing from concave up to concave down. And this one doesn't have, I graphed in the second derivative myself. So if we graphed in the second derivative, where we have that inflection point, it would be an x-intercept for the second derivative. So the derivative of function is the slope f prime of x at a given point. Therefore, a graph of f prime of x will show the slope of f of x on any identified domain. Below we have the graph of the function y equals x squared plus 3x plus 3, and its derivative y equals 2x plus 3 in red. Okay? And you have this in your notes, and I have most of this up here with a little bit of it blocked. There we go. All right, so where our function is decreasing, the derivative is below the x-axis. Where we have a relative minimum, we have an x-intercept for our derivative. Where the function is increasing, the derivative is above the x-axis. All right, so the local extrema of the original function, where the slope is 0, is where the derivative has its x-axis intercept. When the slope of our function is negative, the derivative's graph is below the x-axis. When the slope of when the slope of the function is positive, the derivative's graph is above the x-axis. So when we're decreasing, we're below the x-axis. When we're increasing, we're above the x-axis. Therefore, if the derivative's graph approaches the x-axis from below, the original graph is nearing a local minimum. If the derivative's graph approaches the x-axis from above, then this is where the function is nearing a local maximum. In the example above, the derivative has a 0 when x equals negative 1.5, because this is where our function has a local minimum, because we're going from decreasing to increasing. So that would be a local minimum. Okay? All right, so I'm going to save this one, and we're going to do this one together in class. So I'm going to skip over this one. But I'm going to go over the ones I have in the notes here that you can print out, because I have these ones all complete. So we'll do that other one together. All right, so here I have the question, and one of the reasons I say that these will make really good notes for you is that not only do I have the what, I have the justification. So when you're answering the why, here are examples of things you can say for the why. All right, so on what open interval is our function increasing or decreasing? Justify. So the function is increasing from negative, and I have it color-coded too, so I don't even need my moving arrow. The function is increasing on negative infinity to 2, from 4 to 6, and from 8 to infinity. Justification, the first derivative is positive, negative infinity to 2, 4 to 6, and then again from 8 to infinity. Question B says, at what values of x does f have a local maximum or minimum? Justify. We have a local maximum at x equals 2. Justification, first derivative is positive for x less than 2, and negative for values between 2 and 4. And I should add one other thing. I should have added in that f prime of x is 0. All right, so our first derivative is positive for less than, negative for between 2 and 4, and f prime of x equals 0 at x equals 2. Right. We have a local minimum at x equals 4. Our first derivative is negative from 2 to 4, and positive for 4 to 6. And let's see, let me look at that. 2 to 4 and 4 to 6. I want to make sure we weren't in that big area with the gap. And we have and f prime of x is 0 at x equals 2. X equals 4. And so when I post this, it'll be posted with the additional stuff because I haven't posted it yet. All right, and then we have one more. We have a local maximum at x equals 6. First derivative is positive for between 4 and 6. Negative between 6 and 8. Critical points occur where the first derivative is 0 or undefined. So here, f prime of x is undefined at x equals 6. You have a gaping jump there. Come on. Toot, toot, toot. Well, that'll look like a 6 later. So notice there we go from increasing, decreasing to increasing, and our first derivative is going to be undefined there. By the way, this is not the graph of the function. I should have mentioned that. This is the graph of the derivative. I'm hoping you can see that. It says derivative there, but it's kind of light. So this was the function of the graph of the derivative. So the derivative, not the original function, has a big gaping hole. And so it's not increasing or decreasing when it goes up or down, right? It's when it's above the x-axis or below, because this is the derivative, not the original function. Okay? So we have some kind of break in our derivative there. So we're undefined. But we can have max and mins where we are undefined. Right? So we have sort of a local max there at, now I'm kind of wondering, let's do this, because it's not clear whether that's a filled in point or not. So let's do that, and then we have a filled in point, and then I feel a little bit better about that because it's kind of hard to tell what that was. Right? So now it can be a local max, because notice at 6 we also have something happening at the other end. So let's call this one over here an open circle, and now I feel better about that. Oops, where's my open circle? Come on, board. Open circle. There we go. Let's do that. Now it's clear. All right. Let's look at, wow, 27 minutes on one podcast. Let's look at concave up and concave down. All right, so so here, this is still the graph of the first derivative. It is not the graph of the second derivative. All right, so on what open intervals is our function increasing? We already answered that, sorry, ABC. I needed more space, and I wanted to highlight additional information. All right, so at what intervals is f concave upward or downward? Justify. So the function is concave upward on 3 to 6, the green, and from 6 to infinity. Justification, the first derivative is increasing on 3 to 6 and 6 to infinity. Right? Function is concave down on negative infinity to 3. Justification, the first derivative is decreasing on negative infinity to 3. So notice that if your first derivative is increasing, your function is going to be concave up. And where your first derivative is decreasing, your function is going to be concave down. Right? And let's make sure, let's put that right in your notes. Right? So that's very clear. Make sure you write it somewhere. If f prime of x is increasing, not necessarily greater than 0, right? I can be below the x-axis and be increasing, right? But where the derivative is increasing, and so ignore so the increasing, decreasing there was for the function, right? It's increasing everywhere the derivative is increasing where it's green, and the derivative is decreasing where it's blue. Those increasing and decreasing words had to do with the function, not the derivative. So your function, where your derivative is increasing, the function, f of x, is concave up. And where f of x is decreasing, f of x is concave down. take the coordinates of the points of inflection. All right, so I can state the x-axis, but not the y, I mean the x-axis, the x value, but not the y value, because I don't have the function, I just have the derivative. So we have an inflection point at x equals 3, because our first justification, our first derivative has a horizontal tangent line at x equals 3, and the first derivative changes from decreasing to increasing at x equals 3. So where your first derivative is changing signs, you're going to have an inflection point, right? So where f prime of x changes signs, I shouldn't say changes signs, that's not a good way to put it. Changes from increasing to decreasing, because we're not doing a sign chart here. Changes from increasing to decreasing, or decreasing to increasing. Here, I'll do the shorthand way. F of x, not f prime of x, f of x has an inflection point. Okay. All right, so there's some information. And by the way, actually, you don't have to actually write it down, because or either write it down or print these out. Or maybe I'll print them out for you. Should I be nice? Yeah, I'll be nice. I'll print these for you. All right, so I'm going to print these ones that are all filled in for you, because I am that nice. All right, so here is the last part of this. All right, so on what opening we left off at, I keep forgetting, we already read some of the questions. E, assuming that f of 0 equals 0, sketch a graph of f. All right, so how do we sketch the graph? All right, we're going to use our slopes. All right, so we use the slopes of our tangent lines to get the values for our function, to find where it's increasing or decreasing. All right, so it's a little rough sometimes finding these slopes, because you're looking at just a moment in time. But right at the beginning of the function, it has about a slope of 3 for that very, very sharp part there, because for about a third of a unit horizontal, it's going almost a full unit down. So it slopes about 3 there. It's starting to then it's about 2, and it's about -1. That one really looks like -1. In between those two, right below the x here. Follow the arrow. Right there, definitely -1, and then a +1, right? I think this one's coming over here. If that says -1, it should say +1. If it's referring to this, this is a slope of +1. That's probably just a typo on that. Oh, wait, silly me, silly me, silly me. This is the derivative. This is the derivative. Ah, not the function. Oh, silly, silly me. Silly, silly me. I tell you, I'm getting tired. Ay, ay, ay. There we go. This is the derivative, not the function. The values on our derivative are slopes. So right here at 0, 0, 3, right? That's a slope of 3, because the value, let me write it this way. This is even better. You can just tell I'm getting tired. F prime of x, f prime of 0 here, it says 0, is 3, right? So that's why our slope is 3. You know what, this is a pretty long tape. I'm gonna stop this tape for right now, and I'm gonna pick up, and I'm gonna go over this little section, and that way the tape won't be too long. All right, so bye for now, and I'll pick up on the next, with the rest of this graph on the next section, and it won't be very long.